Prelab number 2, Newton's law of cooling. In this lab, we will study the rate of heat loss. And this is the rate of cooling to the environment. From a, let's say, hot object. So the way we define this is we look at power, and we define power with P, and then it's the power, the rate at which heat is dissipated into the environment. So what we're going to do here is that we're going to have a cup of water where the temperatures are going to be warm, hot, and cold, all from tap. So we're going to start with water. And so when I say water, warm, hot, cold, in a paper cup. Now note that this paper cup comes in your lab kit that transfers heat into the room. Now there's three processes that actually, or three mechanisms, I should say. Okay, so there are three mechanisms to do so. So the first one that we've talked about is that we talked about conduction. So conduction is the heat loss through the paper cup walls. So if I think about a paper cup, you could imagine that inside the cup, so how about if I have my cup over here? Here's my cup, and we want to show thickness to the cup. So I'll just say that this is the thickness of the walls. So what this cup does is it contains hot water. But note, we're going to vary the temperature of this water. So right here, this is going to be the temperature of the water, and then the walls of the cup, here in gray, is what comes, it's the heat transfer through the walls of the cup. So when you look at this in detail, and by the way, we should also say that out here is the environment or the room that you're doing this in. So when I'm looking at this, I'm going to have heat transfer because the temperature of the water, and let's say the temperature of the room, we expect here that the temperature of the water is going to be greater than the temperature of the room. So what do I mean by that? So if I look at heat conduction, we don't want to get too much into the details, but here's what we're seeing here. I have a thickness of the paper cup wall. And on one side, This is the hot water, and on this side, there's the air. So in other words, here's the hot water. This is the cold room. And what we're going to have here is that we're going to have heat transfer that's going to go through the paper cup and into here. So again, this right here, this is the paper wall. You could see here is that this guy's going to have some thickness. And what you also see here, which is really hard to see, is that there's an area right in here. There's a contact area. And so then this here has to do with the area. So when I say paper wall, that really means that this is a material dependence. So when you look at this type of heating or heat transfer, we say that this heat transfer is then going to be a material dependence. It's going to depend also on the area. So if I have a bigger area, I'm going to have more heat transfer. And the thicker the wall is, the less heat's going to transfer. So it should depend also on the thickness of the wall. And then it should depend on the temperature difference. That is, if I have a hotter fluid inside the cup and a colder room outside, I'm going to get higher transfer if I had a lower hot water temperature and a warmer room temperature. So it should depend on temperature. So the material dependence is known as the thermal conductivity of the material. And so this type of heat transfer is the warmth when you hold a cup of hot tea. So in this case, what you're seeing here is that there is heat that is being transferred from inside the cup to outside the cup. And this process is what we call conduction. So if I look at this guy here, here's what I have here. The second type of heat transfer that I want to talk about is that I want to talk about radiation. In radiation, this is the heat loss due to infrared waves, sometimes known as heat waves, from the object. Now, as an example, by the way, I said infrared, but it's really any electromagnetic waves. Okay, infrared is just one of the types of them. So what I'm seeing here is that as an analogy, to give you a sense of what's going on, we have an incandescent. These are the light bulbs that people want to get rid of. Bulb. So what does that mean here? So the first thing that I want to look at is that what do I mean by the bulb? So if I have a bulb, then let's say that it's going to come into the socket region, right? So if I look at the socket region in here, then you'll see that it typically tapers down, and then you'll have the ground right there where it connects. That's one of the connections points. And then you'll see that here's how you screw in the light bulb into this here. Now what happens here is that you can have a glowing bulb. So if you have this glowing bulb, the way you get it to glow here is that you get a filament that gets really hot. And, you know, just for your information, the temperature of a bulb, an incandescent bulb, and I think it's 100-watt bulb, the temperature of an incandescent bulb is about the same temperature as the surface of the sun. So when you look at an incandescent bulb, it's like holding a tiny piece of the sun because they have the same temperature, and therefore they have to emit the same electromagnetic spectrum. But they're not exactly the same temperature, so you'll see that they're slightly off. But both the sun and the bulb emit copious amounts of infrared light. So here's what you find. In order to get this light bulb to work, there's a vacuum inside the bulb. So this means here is that there's no conduction, since there is no material. It's a vacuum. As a consequence, that constant, that thermal conductivity value is exactly 0. So the only way to transfer heat is through infrared / heat waves. So if you put your hand outside, I mean, you don't want to touch it because it gets really hot. But if you put your hand and you're not touching the glass bulb, you could still feel the heat of the bulb. And therefore, what's actually happening is that there's heat transfer here, and this is what we call radiation. This is what we call the infrared heat waves. So in this case, if we go back to the cup, there are waves that are being emitted from the cup because it's hot, just like the light bulb. And in this situation, that type of heat loss is radiation. Now, there is another one that doesn't, there's several other ones. The other ones that we can look at here is that there's one called convection. And convection, what you're finding here is that you have heat loss through the air via convection currents. And I won't say very much about this, but here's what we do know. you probably heard that hot air rises and cold air falls. That's the same for the water. So what happens here is that if I have the surface connected to the hot water, that air cools that surface. As a consequence, that cool water flows downwards to the bottom of the cup. And as a consequence, it displaces hot water, which then floats up to the top. But then that cool water, that water gets cooled by the air. And what you see here is that you end up getting a flow of currents here. So if this is my cup right here, you then have a buoyancy where the air here, right? So the air cools the surface. And as a consequence, you now create this flow of water, and these are called convection currents. Now, this is exactly what you do if you have a really hot cup of coffee or a really hot bowl of soup. You take your spoon and you have a tendency to pick up some of the soup, and then, by stirring it or taking some out and putting it back in, you can, as a consequence of that, you then get heat flow that literally comes out from the water into the air. And the more you cause convection currents, the quicker the heating. So those are typically the standards of the way heat loss. Well, there is a fourth, it's called evaporation, which I won't talk about, but it is about, you'll see it's quite interesting when we talk about it in the next chapter. And so what we want to study today is that, I'm going to say that there is a fourth way to model heat transfer. And this is the one that I want to talk about. This is called Newton's law of cooling. So Newton's law of cooling is very similar to conduction. And so what you're going to find in today's lab, so in today's lab, you will start with warm water. The water that I got from my faucet was 40 degrees centigrade, or Celsius, excuse me. That is about 4 ounces. So this means this is half a cup. Could it be 5? Yeah. Could it be, 3? Yeah. I just used 4 ounces so that I could give you that. So what Newton's law, very similar to conduction, is it tells us this here. Newton's model states the rate of heat loss is proportional to the temperature difference. So in this case, it's going to be the temperature difference between the warm water and the cool environment. So if I look at this thing, so remember the rate loss, as soon as you say the word loss, then we're talking about a cooling effect. So here's what we're talking about. So I know that the power is dq dt, that's the rate at which energy is transferred. But in this case, we're going to give it a negative sign because we know that it's cooling. So one can see where I'm coming from this is that I know that heating is typically given by Q equals mCt. Now, if I put this into the derivative term, I'm assuming that the mass and the heating, the heat capacity, well, we're going to say here is that this guy now becomes proportional to minus dt, capital T, dt. And then this tells us now, so now if I go to Newton's laws, Newton's cooling law, it says this temperature difference is, you know what, I'm going to take that minus sign out and I'm going to put it on the other side. So here's that minus sign. From there, that there is a material property. Okay, so this is going to be some thermal constant that is material dependent. So it's a stretch to go, well, it's got to have some amount of mass. So in each case, make sure that you use the same amount of water. So if you start off with 4 ounces, stay with 4 ounces. If I have the same material, we would then say that the heat capacity would be the same. So it's a material dependent quantity. But what Newton says, it's the temperature of the water minus the temperature of the room. This is Newton's cooling law right here. Newton's law of cooling. And that's what we want to look at. So now if we solve this mathematically, right, we can mathematically solve by integration, right? This is just an integration equation. So if I look at this guy, this is going to be dt. So the derivative of temperature with respect to time, and that has to be minus k t. So now what I'm going to do here is that I'm going to do a little bit of algebra. I'm going to take the temperature into the denominator of the left side and the time onto the left, onto the right, excuse me, and I'm going to integrate from some initial temperature to some temperature t of dt over t, and then I'm going to get minus, and I'm going to start my clock at 0, and I'm going to go to some time t of k dt. Now, if I integrate this thing, this tells me, so now I have some type of integration. And the integration then tells me that this is what? The natural log of t over t naught. And this will equal minus kt. So then if I take the exponential of both sides, the solution to Newton's cooling law is then going to read the temperature as a function of time is going to be the initial temperature times e to the minus kt, where T naught is the initial temperature of the water. That is the solution to Newton's cooling law. So if I plot this, you could see that this is an exponential decay. So what I'm seeing here is this initial temperature is the initial temperature of the water, whether it's warm, hot, or cold. So then if I look at my graph, it's going to look something like this here. So this is the initial temperature of the water. And then right here, this is the temperature of the room. So what I'm going to see here is that this guy is going to then exponentially decay to the room temperature. And what we're going to find here is that I'm going to label a point that this is the time to reach room temperature. And this has a significant name. It's known as 5 tau. So if you've taken electricity and magnetism, you might know what that means. But for right now, I'm going to assume that you don't. So let's not talk about that any more than that. So here's Newton's predictions, which I want you to check. So here's Newton's predictions. Newton's law predictions. So the first one here is K. So if I look at the material dependence, is completely shoved into K. Now, so when I look at this thing, I could say the following thing. Since we are only dealing with water, then the thermal constant which we've defined as K here, should be a constant, right? It should be a constant. So the way we see this here is that we're going to look at something like this here. So if you look at the equation, we could see here that the ratio of temperature to the initial temperature, this is going to be equal to E minus KT. But the way we defined time is we redraw this thing and we say that this is T over tau, where tau in this case, which is 1 over K, is defined as the time constant. So this is our time constant. So here we go. So if you parameterize the curves in Google Sheets or what's it called? Excel, using the exponential, parameterization, you can pull off the time constant. So if I look at this thing, here's what we should be seeing here. So if I have warm, hot, cold water, and I look at this K value, which is 1 over the time constant, then what we should see here is that for these values right here, I would expect that this, and this should be close in value. The question is, are they? That's something that I want you to check. Now, the other thing that we want to do here is that, we want to predict the time it takes the water to, now remember, when I say water, I mean what? Warm, hot, cold, the water to reach room temperature. So what we said earlier here is that this time is called 5 tau. In other words, it's called 5 time constants. And in this case, this should be 5 times 1 over k. So if you figure out what k is, then this is how much time it takes to reach room temperature. So then we could ask the question, why is this so? So look at the ratio T temperature as a function of time divided by the initial temperature. So equation-wise, it looks something like this. So at T equal to 0, I have T of T equal to 0. And so if I look at this here, this is going to be my exponential, which is minus T over tau. So at T equal to 0, I get e to the 0. So I get exactly 1. So that means initially the temperature of the water is exactly the temperature of the initial temperature of the water. Okay, so this tells us that this is 100% of T naught. Not a surprise. We started off with the water at that temperature. But now at T equals to 5 tau, if I look at the same ratio, then I get e to the minus 5 tau divided by tau, and this gives me e to the minus 5, and this number gives me 0.007, or this is going to be 0.7%. So what does this tells me here? That when I look at my graph, and if this is room temperature right here, that if I start off at a point right here, at T naught, this will decay to 90 99.3% of its value would have decayed to the room temperature value. So this means this is the 5 tau that tells us how quickly you get to room temperature approximately. So if I was to write this, it says this: the temperature has decreased. But the common language really means that it decayed to 0.7% of its initial value of T naught in a time of 5 tau. In other words, the water is at room temperature at this time. Okay? So those are the things that I want you to check for all three graphs. So here is what I want you to turn in. Okay? So let's look at that. So in part one, I want you to do what? I want you, so before doing the experiment, predict how the cooling curves, of what? Of warm water, hot water, cold water will look like on the T versus time curve. Make sure you plot all three on the same graph. Okay? Plot all three on the same graph. Now, explain your reasoning in short, concise sentences. Then go to part two and do the experiment. So now in part two, here's what I want you to do here. Now, experimentally, measure the cooling curves. So this is important. So the first thing that you got to do here is watch first John's video. Who is John? John used to work at my college, and he was the lab guy there for several decades. He's a very, very close friend of mine. So watch first John's video to understand the process. Then what you're going to have to do is download Tracker. Tracker is the most widely used software to get data from videos. And by the way, it's safe. They have conferences on Tracker. And by the way, the guy who wrote Tracker came from, he was one of the guys teaching with me. In fact, he's probably my most, he's definitely my mentor. He guided me in how to teach at a community college. And then finally, you will need warm water. So I'm talking about four ounces at about 40 degrees C. And then, by the way, you're also going to need hot water and cold water. Okay, and then any thermometer. When I first did this, I did it with my household thermometer. In fact, you don't need any part of the lab kit for this. So in this case here, the lab kit has a thermometer too. And then finally, you're going to need a cell phone to record the data or to record the video. Okay, have fun. I think this lab is light compared to the last one. If you need any help with anything, let me know. Come by and see me.